kVA rating of this particular transformer. And then next what we have to collect is like we have to collect the leakage reactance of the transformer, like HV to LV, LV to TV, and LV to TV. Like this we have to get the value of the leakage reactance from the customer. Okay. And other than that, what we have to collect is like we have to collect the bill of the particular equipment. It has to be for both lightning as well as switching impulse levels.
Yes.
Okay, for lightning we will be getting the like these values, and for switching we used to get these values. Okay, we will see what is the difference between the switching and lightning, why the bill is different for lightning and why the bill is different for switching. When we go for SFO studies, we will see in a detail. Okay. Now we are seeing, what we are seeing is like what are the data which we have to collect from the customer. This is what we have been seeing. So these are all the data for lightning and switching bill we have to collect from the customer. And after that, what we have to do is like power frequency withstand this data we have to collect. And the other important one, important data which we have to collect from the customer is these values, like this capacitance values, capacitance between HV to ground, LV to ground, and TV to ground, like these values which we have to collect from the customer. Okay,
this value,
this will
sorry, the value of capacitance, like these things, LV to ground, HV to ground, LV to TV.
Yes.
This does not come of a standard or a like
yes,
a general value.
there is a yes, in standard they have mentioned some formula to find out the values. Okay, to find out the values. Just a minute, I will show the formula too. Just a minute, I will.
You can leave it, Bankard, if it's taking time.
Yes, I have found one.
Okay.
Just give me.
No worries.
Okay, I will find another snap of it when I'm after
Yeah,
the
please.
session.
Yeah, no problem.
I will show. Can you see my screen?
Yes.
This is a snap. This is a standard IEC 60071 port 4, which we generally use for the insulation coordination. Okay. What is the use? What is the disadvantage of using this standard? Is like they have mentioned like it can be used for two winding transformers. Okay, where the transformer's internal voltage or transferred voltage from LV to HV or HV to LV we can calculate using the way which they have mentioned here. Like using this formula, we can find capacitance of auto transformer can be computed by the following formula. Like this, with this value, we can find the value of capacitance if the customer has not given, but it has to be collected from the manufacturer.
Yeah.
Okay,
In
it
the
has
right
to
way.
be collected from the manufacturer. Yes, for performing lightning studies. For high frequency studies, like other studies also, for TRV studies, we have to collect it from the customer. Like that, what are the studies? Like for lightning, for VFO4, and for TRV studies, we have to collect all those values from the customer. Okay, if you are performing these three studies, then we should not go into the study without these values. Okay.
Okay.
This capacitance value we have to collect it from the customer. For whatever the reference you might take, you can find the values for the two winding transformer. But if you have three winding transformer like this, like auto
Yeah.
transformer or three winding transformer, then we have to collect it from the customer. There is no other way to go. Okay.
Okay.
If you are not able to collect it from the customer, then we have to say we have taken it from the previous reference or previous project reference. We have took this value, like that suggestion. We have to tell it to the customer. Okay.
All right.
Yes. This value is how we have to get it from the customer, like capacitance to ground, HV to ground. We have to collect these six values. We have to collect it from the customer. Okay, these six values we have to collect it from the customer, and other details like saturation characteristics, which will be useful when we are performing transformer energization studies. Okay, when we are performing transformer energization studies, then we have to collect these data like air core reactance, knee point voltage, magnetizing current, and interest decay constant. These are all the values which are all most important to perform the studies. On our scope, we don't usually go for this tab changing and all. Our the data which we want is like these are all the data which we have to get it from the customer. Okay.
Okay.
Other than that, what we have to collect is like we have to collect the what do you say, that the worst case inrush they have calculated inrush current data which we have, which they have calculated, which they have calculated in the site. I will show. Okay, this is the peak inrush current. Okay, they have calculated in this in the most unfavorable condition. Okay, like this data which we have to collect it from the customer. Okay, why we have been collecting this data is like we have to match the inrush current, peak inrush current, which is happening in the transformer during energization. Okay, before taking our transformer into the studies, what we have to do is like we should try to match the peak interest current which is given by the customer, and then we have to implement that transformer in our studies, and we have to perform the studies. Okay, for
Okay.
like transformer energization studies. This part I will will show now when we are going to perform that transformer energization. Okay,
Yes.
this data we have to collect it from the customer. Okay, this peak interest current values. Okay, then these are all the data which we have to collect it from the customer for the transformer. Okay,
Yes.
then I will transformer. This is an auto transformer. This is an auto
Yeah.
transformer. This is a three winding auto transformer. Where I have took it is like I have gone inside this. Here can you see this? This is an auto transformer. This is three
Your
winding
screen
auto
is
transformer.
your
This is
screen is
two winding.
frozen, mate. Hello.
Frozen.
Uh,
Hello.
Venkatji, we can see only the PDF. The PDF.
Yes. The highlighted PDF only
Yes.
that we
Yeah.
can see. We can't see another one.
So we can't see the SLD, it seems.
Oh, okay, okay.
There is maybe delay, or you are just sharing the screen, no
I hope now
desktop.
it is. I hope now it is visible.
Yeah, but it's still the same PDF, the
Yes.
highlighted one. Yeah.
Now?
Now I can see PSCAD. Yeah.
Yes. 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 the three winding transformer where I have took is like I have gone inside the main library, and when we go into the transformer category, there you can find the three winding auto transformer. Or if
Okay.
you want some other transformers, here you can find like three winding normal transformer, two winding transformer like this we can find. Okay, four winding transformer like this also we can find here. Okay.
Okay.
uh, then what we have to do is like we have to give the values which we have collected from the customer inside the inside the transformer. Okay, like what
Yep.
is the MV of the transformer and frequency and leakage reactance. Like we have seen the leakage reactance here, right? In
Yes.
percentage they have given, in per unit they
Yeah,
in
that's all.
percentage they have given. It is in percentage, but we have to plot it in per unit. Okay.
Yep.
Okay. Yes. How we have to do? If it is 19% they have given, then we have to enter it as 0.19 per unit. Okay.
Yeah.
For leakage reactance. Okay. Like this, what we have to do is like we have to give the values for leakage reactance for HV to LV. This is for
Yeah.
HV to LV, and this is for HV to tertiary winding, and this is for LV to tertiary winding.
Okay.
Okay.
Yeah.
Okay. And then what we have to do is like we have to give the no load losses.
Yeah.
Okay, we have to give the no load losses. Okay. In this particular example, I haven't took the no load losses. If but we have to collect it from the customer and we have to enter it. Okay, we have
Yes.
to enter values. Okay. And then for ideal transformer, what we have to do is like because we are going to perform transformer energization. Okay, transformer energization, then what we have to do is like we have to keep this ideal transformer model as yes. Okay,
Okay.
we have to keep ideal transformer model as yes. Okay, why we are doing is like when we are doing some switching studies, what we used to do is like we used to put the saturation characteristics as enabled. Okay,
Okay.
saturation we have to enable
Switching.
when we are performing the transformer energization case. Okay.
Okay. Yeah.
But normal studies, when we are performing other studies like temporary over voltage studies like that, then there is not necessary to enable this saturation characteristics.
Right. If we
Okay.
put the saturation characteristics, it's okay.
Uh,
It's not a harm,
uh,
right?
sorry.
My question is, if I have the data, and for example,
Uh,
I'm using the same model, so I can put it. There is no harm, right?
I can't
So so
understand. I can't understand.
so
Fine.
so the question is, if I am doing a
No,
TOV,
Himanshu, I have understood. Yeah, I have
yes,
understood your question. Like means what say, shall I use a typical data for your modeling? That's the question. Answer is no. You have to get a specific project transformer model, and this numbers will have a huge impact on the switching study and transformer analysis. So you need to get this data from the manufacturer specific to this project, and you have to.
okay, no, no. What I was asking, another question is, see, Venkat says, for the saturation, I don't need to model it when I am not doing a transformer energization study. Is that right, Venkat?
Yes.
Yes.
That's
So my
right.
question is, yeah, my question is, if I have the data and if I leave that
Uh,
here for some reason, is that a harm or it makes no difference to
You can
TOV?
give,
Or
I mean, Venkat, what he's saying, if he has the data and if you're not really performing transform annotation, still shall I enter the data? He can
yeah,
get
yes,
nothing
you
wrong.
can, you can enter the data. You can
Yeah.
enter the data.
yeah, there is no negative impact of it. That's
No,
what I'm
no
asking.
negative.
Yes. Just what we have to do is like we have to keep it as no. That's it.
Okay,
No. Yeah.
okay,
Okay.
okay.
Then we don't take these characteristics into account.
All right,
Okay.
right. Okay,
Yes.
sure, understand.
And then what we have to do is like why we are keeping. This is one necessary point which we have to discuss. Whenever we are performing this transformer energization, what we have to do is like uh, we have to give this saturation as enabled, and what we have to do is like we have to give ideal transformer model as yes. Okay,
Okay,
this is one important point. What we are doing is like when we enable this saturation, what happens is like transformer will have some what do you say, that some magnetizing characteristics like during energization, right?
Yes.
It will draw some huge current during magnetization, right? During
Yeah.
energization. Okay, I hope
Yeah, I know that. Yeah,
you don't know.
destabilize the core.
Yes,
Yeah.
yes. It will draw
So
some
if the
huge current.
saturation is there, then it is not an ideal transformer, as simple as. Correct. No, ideal transformer is
Yes, sir.
just
Yes,
transforming the voltage. Say example, if it's a
yes,
220 bar 11 kV, it's plainly transferred 220 bar 11 kV,
yes.
assuming that there is nothing, no loss, etc., no saturation, etc.
No,
So,
yes,
I
sir.
mean, if the
During
transformer is not ideal, then it has, I mean, so say everything else will come into picture.
everything else will come into picture. What is happening is like the current which is drawn during normal operation will be much lower. Like it will be in 1% range, or else it will be below 1% range. The amount of current which is drawn during normal operation. Okay, this is what the difference it creates. So what we have to do is like we have to create both the option as yes.
Yes.
Okay, but what they have been suggesting is like if we keep this as no, and if we have kept this as saturation, what it does is like it will take both these values, like it will take the values from saturation and it will take the values from the configuration from the ideal transformer also. It will create some duplicate values in the matrix which they have been using to solve the transformer. Okay,
Okay.
so that it might produce some erroneous report. Okay, this is what the suggestion that has been given by PSCAN. So
Okay.
what we have to do is like we have to keep this ideal transformer as yes.
Yes.
Okay.
Yes.
Okay. Then what we have to do is like we have to give the tertiary winding configuration, like whether it is in star or whether it is in delta. Then other details is like whether your delta is lagging or leading. That information we have to give. And as I said, there is no need for online tap changer in our condition, so we can keep it as no. Okay, other than that, next is like the winding voltage. This is I hope this you can fill it simply,
Yes.
like what is the RMS voltage which is given for the particular transformer. And then next we have to go for the saturation. As I said, these are all the values I have told about the air core reactance, right? We
Yeah.
have to collect it from the customer. This interest decay we have to get, and the knee point voltage and time to release fluxing is, it won't be a big impact, but we have to collect all those values. Other than that, okay, other
Okay.
than that, what we have to collect it from the customer. And another important point is like the saturation, where we are placing the saturation winding. That is more important. Okay, where we have to place the saturation winding is that the winding which comes near to the core of the transformer. Okay, we might have seen the core of the transformer, like in the pictures
Yeah.
we might have seen,
Yes.
right? Okay, what they generally do is like they will have they have the core, and next to core, what they will do is like the low voltage winding will be coming first. Okay,
Okay.
during winding. Okay, after that, what they will do is like they will go for the high voltage winding. It all on the construction features I'm talking about.
Yes.
It all
Yes.
on the construction features. Okay, then what we have to do is like we have to place a saturation on the winding which is near to the core. Okay,
Okay.
so that I have placed the winding which is near to the core. Now my tertiary winding is near to the core, so I have kept it as tertiary winding. Okay,
Yes.
tertiary as near to the core. Okay, and then we can perform the studies now. Other than that, what we can have is like if we are going to take output for the particular transformer, like HV current, LV current, tertiary current. If you want, you can take it from here.
Okay.
Okay. Yes.
Yes.
These are all the data which we have to give for the customer, give for the transformer. And other than that, what we have to do is like if you are energizing the transformer from the 400 kV side.
Yeah.
Okay, what we have to do is like generally what we used to do is like we used to keep the this is what happens in a real time also. We used to keep the secondary side on the other side with the open circuit, right? It will be an
Yeah.
open circuit, so that in order to avoid what we say that in order to avoid that's sorry, in order to create the scenario, what we are doing is like we have been closing the circuit with a huge resistance. Here you can see that this is a huge resistance. It is about e power 12 value.
Yeah.
Okay, this is an e power 12 value. It is an in ohms. Okay, what we have to do is like we have to take a resistor and we have to ground it with a huge resistance. Then it automatically it will act as an open circuit. Okay, it will automatically act as an open circuit. If you are not connecting this, what it will do is like it will show some error like termination has been done incorrectly, like this. It will show that it will throw some errors. Okay, in
Yeah.
order to avoid that, what we are doing is like we are closing this circuit with a huge impedance. Okay.
Yes.
And
that star side is only simple earth, right?
yes, it is simply earth.
Okay.
That's a solid electric system, no? Like
Solidly
high
earth.
voltage.
You
High
don't need to
voltage.
give any value there in this particular example.
Sorry.
In this particular example, you don't need to give a resistor value for the star, just earth.
Yeah,
Yes,
that's what I'm
yes,
telling. Like it means 110 kV and above means predominantly we go with the solidly grounded systems.
Yeah. The question is, you don't need to put a like a resistance value there. Like for example, is earth to 1 ohm 1 ohm ground or
No. We just
okay.
means if it's a solidly electric system, we just means also directly connected to the ground.
Connected
Like
ground.
earthing,
Okay.
you will take this detailed resistance, but that is not really needed for this installation.
Okay.
And other than that, these are all the
And
data
only
which we
means Venkat, you just go inside the transformer. Only one point I think like that has to be made it clear is like here when you are giving a leakage reactance, you are giving it on a base MVA, and probably means what say if they have given the impedance on a different base MVA, then you need to know how to convert that into a common base, right? No.
common base value.
Yes.
Yeah.
Yeah.
So like
Yeah.
means what say if it's a 10% on like the transformer rating, like means what say because tertiary rating will be much lesser. You got the
Yes.
point now. And
Yes.
here also means what's the value which they have given. This is actually a requirement. That's all. Means that's how
Yeah.
we have to understand. Like means what say transformer rating is 500 MVA on both HV side and LV side. Correct? No,
Yes.
that is like 380 and 132 kV. 13.8 kV means what to say? It is they are using it for auxiliary purpose of this substation. So they have means given as 2 MVA. But in a
Yeah.
reality, like when the manufacturer manufactures with the star grounded auto transformer with the means what say delta, he cannot
Yeah.
really, even if he tries, he cannot manufacture with the 2 MVA. That rating will be at least like means what say typically it will be like 1/3 of the main winding. So
High
that is
voltage line.
could be like as high as like 150 MVA. But nowadays
Okay.
the optimized designs etc. is coming. But still means also it will be in the range of maximum 1/6. It cannot go below 1/6. You got
Okay.
the point, you know, like at least 500 MVA, it needs like at least 75 MVA is the bare minimum requirement of this. Below 75 MVA, you cannot go it. Here they have given 2 MVA just because means also the customer has asked it's a 2 MVA. That's all.
Okay.
Yep. And probably you can look at this HV to LV, the impedance is like 19.85, whereas the HV to TV and LV to TV, it's extremely high. That is extremely high. That's because like means what say when they are trying to convert that to 500 MVA base, then this becomes high. Because means if you want to test this with the what do you say? If you want to test this with uh, delta winding, then you cannot load the delta winding beyond its rating. Correct? No. So
Yeah.
means whenever you are doing a short circuit test for a transformer which is multiple windings, and if you are doing for a 2 windings, then what is the lowest winding rating? Only up to that you can load it when you are doing a short circuit test. So that means
Yeah.
like when you are doing a short circuit test, the impedance you found out is the impedance based on the lowest winding rating on these 2 windings which you are doing, like HV to LV or HV to tertiary or LV to tertiary, whatever it is.
Okay.
But when you are converting that into, what's a 500 MVA base, like in this case, then that impedance will be increasing exponentially. That's the reason why you are getting a huge value.
Right.
Yes, Venkat, please.
Yes, this is how. I hope you know how to convert this.
Yes.
NK,
Yeah, we had that
uh,
session. Yeah.
yes. Okay. Then what else? Yes. Other than that, what we have to do is like I hope in the previous section you have gone through this multi-run component. Yes, I hope
Yes.
Google might have taught you. Yes.
Yeah.
What are the options which we have seen with this multi-run? Can you tell me?
Yeah, just a number of the multiple run you want to control, enable or disable, and we only discussed one which was sequential.
Okay, okay, okay.
Yeah.
You have done only sequential, right?
Yes.
Okay. I will show other one example. Just, here, can you see this? This is what you have
Yes.
seen. You might have seen, right? For
Yes.
sequential, right? Here
Yes.
you might have kept it as enable,
Yeah.
okay. And
Yeah.
other than that, you might have kept this value as
Sequential.
sequential.
Yeah. And then
Yes.
two variable. Yeah.
And
And then we need to enter
yes,
the increment period for two variable in separate window. Yeah.
to yes, this is what
Yeah.
I have done now. Here you
Yeah.
can see this. I have set the
Yeah.
range of 0.3 to 0.31, and I
3 1.
have
Yeah.
kept an increment as 0.01.
0
Okay,
0. Yeah.
and
Yeah.
yes, and other than that, what we can do is like here we can use it to perform. Uh, I hope he might have also explained the way, which are all the inputs to this and which are all the outputs to this
Output
multi-run.
to this. Yeah. Yeah. Yes. Yeah.
This
Apart
is
from that control system.
yes, which
Yeah.
we what we have to do is like in right side we will be having all the inputs to the multi-run. Okay,
Yes.
in the left side what we will do is like we will take all the output from the multi-run.
Multi run. Yeah.
Okay, yes, multiple run. Okay, if you want to enable this if you want to disable this multi-run, what we can do is like we can just keep 0 to this value, and we
Yeah.
can disable this multi-run completely. If
Yeah.
you want to disable it completely, not even taking the values which are all inside this here, what we have put here. I
Okay.
hope he might have explained this
Yeah.
about
Yeah.
this.
When we disable, we
Yes,
can enter the value. Yeah.
enter the values, right?
Yes.
If you want to completely disable this multi-run, what we can do is like we can just give 0 here, and we can
Yeah.
completely disable this multi-run.
Yeah.
Okay, from our option. Okay,
Yes.
and other than that, what we can do is like there is something called as list option, right? List
Yeah.
option. Okay, what we can do with this list option that we should know, right? What I have done is like in this application, in this project, what I have done is like I have done what I have done what I have done is like to give a fault time. What
Okay.
time my fault is happening. For that,
Yeah.
what I have did is like I have created a scenario for creating a fault. For putting a fault into the system. What I have done is like I have used the sequential one.
Okay.
Okay, at what instant I'm going to put the fault into the network. For that, what I have done is like I have created the sequential one, and
Yeah.
what I have done is like I have given an increment of 0.001. For each
Until.
instant, I have to apply the fault.
Yes.
Okay, for that I have used this multi-run. And other thing what I have done is like here what I have done is like I have
Yes.
used to create a fault type.
Yeah.
Okay, we might have different types of fault, right? We might
Yes.
have line to ground fault. We might have different types of fault, right? When
Yeah.
we go into this help file, here you can see. Can you see this?
Yeah.
This is
Yeah.
the code which has been given by the PSK.
Yes. Correct.
Okay, to
Yes.
create a fault into the system.
Okay.
Okay, to create fault into the system. What I have done is like I have took all these code values like 0, 1, 2, 3, 4, all these values I have to. Okay,
Yeah.
and then what I have did is like to create a different types of fault. What I have done is like I have given the I have taken the
Another variable.
second input for the multi-run. Okay, for
Yes.
that what I have done is like I have kept the list. Okay, I
Yes.
have kept the list. Okay, then what I have done is like I have given the data type as real.
Yeah.
Okay, then this is just a label. This is just
Yeah.
a label, whatever the name you can have. Okay, then now what we have to do? We have to go inside the real variable.
Real variable.
Okay, real variable 2. Now what we have done is like number of runs which we are going to give for the variable that we have to define.
Yeah.
Okay. Now in this example, what I am specifically performing is like I am going to
Certain.
perform yes, 5 types of fault.
Yeah.
Okay, 5 types of fault. Okay, for that I have took the codes from the manual
Yeah. Help file.
of the PL file. Okay, now what I have done is like I'm just going to create 5 types of fault. So I have given here 5. Okay, and then what I have to do is like I have to give the values, right, for each type of code for creating a different types of fault.
Yes.
Okay, I have to give the code for the particular fault. Okay,
Yeah.
now what it does is like here it will take how much instance we have given here for the variable one. Here we have given some what is
10.
the value which we have?
10.
Yes, yes, 0.01 is the increment value which we have given, right? At
Yeah.
what it does is like here it will start from 0.3.
Yeah.
Okay, here it will start from 0.3 and it will goes on increasing with the increment of 0.01.
01.
Okay,
Yeah.
yes, till the point 0.31.
31.
Okay, for that complete instance, what will be the fault is like, since I have given the list as 1, it will
1.
be like single into ground fault.
Type
What
1.
is the
Yeah.
respective fault? The fault
Yeah.
that will be the complete scenario for up to this the limit which we have explained here, which we have shown here. Okay, and after
Yeah.
that what it does is like here it will next to jump on to this value 6.
Yeah.
What will
6
be the
value.
fault? Yes, it will
Yeah.
go for 6 and it will do the simulation for all the values like starting
Yeah.
from 0.2 to 0.31. Like this we can use the list option to perform different
Okay.
different cases. Okay, here we
Yeah.
have used list option to create a fault. Yes, yes.
Yeah. It basically taking that fault scenario for each of the sub scenario that you specified here.
Yes, yes, yes,
Okay.
yes. To be more specific, what I can here we have created 5 types of fault, right?
Yes.
Here we have 5 types of fault. Now what we have done is like we have took a particular scenario in a sine wave form,
Yeah.
right? Here we have took just assume this is 0.3
Yeah.
and this is 0.32. This is a single waveform for a 50 Hz system.
Yeah.
For a 50 Hz system, which is 20 milliseconds. Okay,
Yeah.
in 20
Yes.
milliseconds what we have done is like we have differentiated this value from 0.3 to 0.31 as
Yeah.
different values, right?
Yeah.
Different instance with the increment of 0.001.
Yes.
Okay, the increment of 0.001. Now what happens is like it will take one value from this. Okay, let us assume it is 1.0. Okay, it will complete this complete scenario. Multi-run will be performed for this complete cycle for this particular fault. Okay, for this particular fault. Okay, one will be performed.
Yes.
Hello.
Yes.
Yes,
Yes. I can
yes,
hear.
yes,
Yeah.
it will be performed. Okay, after
Yeah.
completing all these scenarios, then what it will do is like
It will go to the
after
next level.
reaching this 0.31, what it will do is like it will jump on to next scenario,
Next.
which is like here I have to if I have to 2.0, then it will jump on to this scenario. Okay, and it will do the simulation for all this
Yes.
full cycle. Okay, and then it will jump on to next value. Like this we can use the list option.
Okay.
Okay,
Yes.
can you tell me how many number of runs this particular simulation will take?
That will take 10 at least. 3. Well,
That
1,
we
2.
yes, yes, I will show.
Yeah, that first one will take 10, and then 1, 2,
Yes,
3, 4, 5, 6,
yes.
5,
Here we have 5 values.
51. 52 run, 51 run.
No, it will take about 55 runs.
Oh, sorry, one for each hire. Yeah. Sorry,
Yes,
I was
one
just
for
counting
each,
one.
right? It will
Yeah.
take
Yeah.
for 10 instance here, and it will
Yeah.
take 5 instance,
5 each,
right?
and
So
then one hire for each. Yeah.
one higher
55.
point. It will do for optimal run. We might have given some
Yes.
optimal
Yes.
run here. Then it will take about 56 runs. Okay,
Yes.
56 runs to complete this simulation. Okay,
Yeah.
this is how the list works. Okay, this
Okay.
is how the list works. If we want to perform different types of fault, we can use this multi-run, and we can perform
List
this
options.
type different types of faults. Yes. Okay, list option. Okay, I hope this option you might know. Yes, for this
Yeah. Yeah.
option.
Yes.
Yes. Okay. And other thing which we have left out is like we have other two types, right? One is
Yes.
one is random flat, and another one is random normal. Yes.
Okay.
Okay.
Yeah.
What does this random flat does is like it will take what do you say that it will take some random values. It will take some random values between the range which we have specified here.
Okay.
Okay, now what
Yeah.
we will do is like I have kept a random flat here. Okay, I have
Yes.
kept a random flat here, and the type
Yeah.
of variable is like real, and
Yeah.
I just this is just a label. This is just a label. What is the
Okay.
scenario I am just creating is like I am just I have took the breaker as three different breakers.
Yeah.
Okay, I have took the breaker as three different breakers. What I'm doing to create is like I'm just going to close the breaker.
Yeah.
Okay, for I'm just going to close the breaker in three different instances.
Yeah.
Okay, here the poles of breaker is like three pole breaker now.
Yeah.
Okay, for each pole, for each phase we will be having a single pole breaker.
Yes.
Okay, for A phase we will be having one breaker, for B phase we will be having one breaker, and for C phase we will be having one breaker.
Yes.
Okay, so there are three breakers. If you want to enable that, what we have to do is like you have to choose yes
Yes.
here.
Yes.
Okay, and then what I'm doing is like I'm just going to give command for this particular breaker. Okay, particular breaker command
Yes.
for this particular breaker from this multi-run.
Yes.
Okay, from this multiple run. Then for creating that scenario, what I have done is like I have took a random flat value
Random
here.
flat.
Yes, random flat I have to, and then what I have done is like I have to go inside the particular variable one, right,
Variable
to
one. Yeah.
to give the function for that. Okay, then what I have done is like I have went inside this variable one, and I
Yeah.
have given the function.
Yeah.
Okay, what is the function which I have given? I have to first choose the range where we are
Yes.
going to perform the simulation. I have
Yeah.
chosen the range from
Yes.
0.5 to 0.52
0.5
is the
52.
range which I have chosen.
Yeah.
Okay, and
Yes.
then what I'm going to do is like I have to choose the instant, right, from
Yeah.
0.5 to 0.52. At what instant I have to switch the breaker? That is the that I have to take, right?
Yes.
For that, what I have done is like I have took some five instance. I have
Yes.
took some five instance. It will be taken randomly. It won't be happening in a sequential
Sequence.
manner, or
Yes.
it won't be happening in a sequential manner or something. It will take some random five values between this range,
But it will do
0.5 to 0.
all the five.
Yes, yes. For it will keep that 5 as a base value.
Yeah.
Okay, if you are taking 0.5, for example, within this range, I am just taking 0.51. Then it will take,
Yeah.
it will keep this 0.51 as a base value. Okay,
Okay.
0.5 as a base value, and following that, what are the operations which we have given for the next? It will do the simulation.
All right.
Okay, yes, okay, and then what I will do is like I have created a scenario like I have explained the sorry, I have given the
Yes.
range for the particular operation, and I have determined the instances, how many
Yes.
instances. Okay, now what we have to do is like we are going to perform some 100 simulations. Okay,
Okay.
100 simulations or 80 simulations or 120 simulations. For that, what we have to do is like here we have chosen some five instant, right?
Yes.
Okay, and what we have to do is like this will be the signal for this particular BT close one.
Okay.
Particular BT close one. Okay, which this is the signal which is going to the breaker one, breaker A. Here you can see this, right?
Yes.
This signal will go to this breaker, and what is the respective number which has been got
BT
from this
closing.
multirun? Yes,
Yeah.
this will be going. This information will be passed on this particular breaker. Okay. This information has been passed for the single pole, right? Now we
Yes.
do have other two poles, right?
Yes.
Okay. For other two poles, what we have to do is like we have to create different instance of closing, right? Different instance of closing. For that,
Yes.
what we have to do is like here. What I have done is like I have took this value as a base, this BT close as base, and I
Yes.
have just incremented with some random value. Okay, with random value. Okay, for that what I have done is like I have used this block.
Yeah.
Okay, what it does is like it will throw some values from here, and some values will be coming from here, and then it will be getting added here, and this
Yeah.
BT close to information will be passed on to this particular breaker.
Okay.
Okay, and this breaker BT close to T, where we will be getting this value? We will be getting this value from this multirun.
Hold on. Yeah.
Multirun. Okay. The same scenario I have done for the third breaker also. For the third breaker also. Okay.
So inside this control system, whatever you are explaining
Yes.
just now. No,
Yes.
no, in the
Yes.
multiple run, in the another one where you are incrementing these values. Can you tell the program
Yes.
what you need to
Yes.
increment?
Yes. I will tell you. I will tell you. Yes. Yes. I will go inside this second variable. Here I have
Yes.
chosen as random normal. Okay, I
Yeah.
have chosen as random normal. I will tell you the difference between random flat and random normal. Okay,
Okay.
now we will see the program what we have done here. Okay, I'm just going inside this real variable
Yes.
2. Okay, real variable 2. Now what I
Yeah.
have done is like I have took as I said in this example. Uh, yes, what I have. Can you wait for a minute? I will just attend this
Yeah.
connection.
Yeah. No problem.
Yes. Can we continue? Shall we continue?
Yes. Yes. Please. Yes. Please.
What I have done in this scenario is like I'm just going to create some 80 instance of information. Okay, 80 instance of information is what I'm going to give for this particular breaker. Okay, then what I have to do is like I have chosen for the first variable I have chosen 5 instances, right?
Yes.
5 instances. Okay, now since I want to create because I want to create 80 instances, what I have to do is like how we can get like 80 instances, like 5 into 4 into 4, if we put, we can get some 80 instances, right?
Yeah.
Okay, 5 into 4 into 4. This is the value which I have given here. Can you see
Right.
here?
Yeah.
Okay, I'm just choosing some 4 instances between this range.
Okay.
Okay, between this range. But what it does is like here, what it is particularly doing is like here it will take this as a reference. Okay, this value as a reference. Okay, then what it will do is like here it will add from the particular value which it has chosen from between this range. Okay, for example, here I have chosen, if I have chosen 0.51. Okay, if I have chosen 0.51, then what I have done is like for the next variable I have given the instance range from 2e power minus 3 to what I have done 2e power
minus 3.
I hope it is minus. I hope it is minus.
Yeah, that's minus.
It is 2e power minus 3 to 2e power minus 3. It is minus 2e power minus 3 to plus e power minus 3. Okay, which is nothing but it is 0.02, right?
Yes.
Okay, this is the instance which this is the range which I have chosen. Okay, what it does is like it will add or it will get added to this value. Okay, 0.51, it will get added to this value. Then what will be the next value? 0.5102.
5102.
Sorry, it will be 512. It will be 512 or 02. Okay, it will just it will be added to this value to be sorry, this is the action it performs inside this block. Okay, inside this block. Okay, then what it does is like the same kind of action I have given for this. I'm just I have chosen some random normal value. Okay, some random normal value for the next variable also, for year variable 3. Okay, for that also I have given the same range of value.
Same range.
Okay, same range, but it does what it does is like it will take some random values, not the particular value which
How do you select this 2e to the power minus 3?
2e power minus 3 is the increment number which you want to do for the particular simulation. It can be
No, I am
any
asking
value.
like what is the logic behind it? It can be any value, right? Whatever you feel is a right interval to increment.
Yes. What we have done is like here we have took some 0. What do you say that? Some 0002 is the value which we have chosen. Okay, here. Okay, if you want some other value, some minute difference between this closing time, then what we can do is like here we can decrement the value. It all depends on what do you say that your need. It all depends on your need. Okay, if you want to use that option, we can perform. Okay, with this. Okay, but generally what I prefer is like don't use this random flat or random variable. Okay, random normal type for performing multi-run. Because why I'm saying is that we might have missed some range of values between this.
Yes.
Right, because it is taking some random values, right? We might don't have get some confidence like it has gone through complete sine wave. It might have missed some instances, but if we go for this sequence, okay, if we go for the sequence or list, what it tells is like it will give you a confidence like it has gone through all the points in the particular sine wave. Okay, for the particular sine wave it has gone through all the simulations that it will ensure that. But if we go for this random flat and random normal, what is the conclusion we might be getting is like we might have it might have seen some values only, it might have left some other values. Okay, so for explanation we will be telling like this is how it will perform all these simulations. Okay, this is how it will perform all this simulation. But what I prefer is like the best option to go with is like we have to go for some sequential. Okay, some sequential and list. It would be the best option. Okay, here what we have done is like I hope up to this point you are clear how
Yes.
it is choosing the ranges for the particular action of the breaker. Okay,
Yes.
this is what it is. It does happens for this type like random flat. Okay, then
Yeah.
we should know what is the difference between this random normal and random flat.
Yes.
Right. What is the difference between this random flat and random normal is like for random flat, what it does is like it will take some random values between 0.5 to 0.52.
Okay.
Okay, 0.5 to 0.52. Okay, but for random normal, what it does is like it will take some input from this range. Can you see this? There is something called as 2.
Yeah.
Okay, what it does is like for random normal, if you are choosing the range as 0.5 to 0.52, okay, what it does is like depending upon the level of accuracy which we have mentioned here. Okay, level of accuracy which we have mentioned here, what it does is like if I am going to give a value as let me say 0. So let me say it is 5.0. Okay,
Yeah.
if I am just giving 5.0, what it does is like it will take the values which are all what do you say that which are all much closer to these values, much closer to this 0.5. Okay, much closer to this 0.5. Okay, and the minimum value will be sorry, and the maximum value will be much closer to this 0.52. Okay, and if we give this value as if we give this value as 1, okay,
Yeah.
if we give this value as 1, what it does is like sorry I have confused. I have confused you. Okay, what it does is like it will be between much closer to this range. Okay, just to
For
take it
one.
as yes, just take it in the opposite way. Okay, if we have 0.5 to 0.52, okay,
Yeah.
0.52, and now I have chosen random normal with the standard value as 1. Okay, now what it does is like the values which have been taken for this random calculation will be much closer to this 0.5, much
Okay.
closer to this 0.5. Now what I have done is like for this instant I have kept it as 5.
5.
Okay, then what it does is like these values will be much farther. This is the
Okay.
conclusion I have. Okay, it will be somewhat
Yeah. One is towards the boundary values, and if you put the higher number, it
yes,
goes
yes.
towards the middle.
It goes away from the point. Yes, this is the
Okay.
difference between the random flat and random normal. I hope you
Okay.
got the point.
Yes.
This is the main difference between the different options which are all available, in this multi-run. Okay,
Yes.
and this I hope you do know about how to perform these options and
Yes.
all,
Yes.
right?
Yeah. Yeah.
You
I
can
know.
here yes, here you can give about 6 channels,
Yes.
okay, 6 channel as input. Okay, 6 channel as input, and the maximum amount of channel which you can took as output is like 6.
Yeah.
Okay,
Yeah.
okay, 6 is the maximum amount of maximum amount of output which we can take from the particular multiple run.
Yes.
Okay, multiple, and other than that what we can here I hope this Gokul
Yes.
might have it, whether you want the you want to
Criteria,
get
the
the
maximum
maximum
or minimum.
values or the minimum values for the optimal run. Okay,
Yes.
that you can give. Okay, now and another option which I want to tell you is like yes, if you are going to perform multi-run,
Yes.
okay, if you are going to perform multi-run, okay, to fast the simulation, to fast up the simulation, what we can do is like here there is something called as project settings, right?
Yes.
Okay, what I can do is like I can keep this channel plot, right? I can keep this channel plot as some values, right? 100 or 250 like that. I can keep. Okay, to make the simulation to run quicker. Okay, to make the simulation to run quicker. Okay, but what the software does is like it will take the output for this solution step only.
Yeah.
Okay, it will take output solution for this particular number only, which we have mentioned in the time step.
Yes.
Okay, now if you are trying to match the output file, which we have got it in a notepad, right? We might have got the output in a notepad, right? You have in the start of the session, you have shown, right? Okay, if you want to match that value with this simulation output value, what we have to do is like for fasting of the simulation only, you have kept this 100. Okay, if you run the same simulation after disabling this multi-run, okay, after disabling this multi-run, what you might get is like you won't get the answer which you have got in the notepad.
Yes.
Okay, which you have got in the notepad. Okay, for that what you have to do is like you have to again change this project settings to 5.
Yeah. Yes.
Okay, to 5. Then you can match the values.
Yeah.
Okay, this is one important point. To foster the simulation, we can keep the channel plot step as 100. Okay, and another option is like if you don't if you are only performing this multi-run, okay, if you are going to get only the data from this multi-run, then you can also do one thing is as like you can take all the channels from the all the channels from the file. Okay, you
Transformer.
can just delete these channels and you can run the simulation. Okay, and after that we can put the channel and we can take the output.
Yes.
Okay, these are all some ways to speed up the simulation. Okay, to speed up the simulation. And other option is like you can run multiple files in a time. Okay,
Yeah.
how we can do that is like here you have to go for this simulation. Okay,
Yeah.
go inside this simulation.
Yeah.
Right click on this,
Yeah.
create new,
Yeah.
and then what we can do is like just to give a name for this particular set and click OK, and then just what we have to do is like include all tasks. Here you can see all the tasks have been added here, right?
Yeah.
Then what we can do is like just click run set and
Yes.
the whole set will get run. Okay, it depends on the license type which you have. Okay,
Okay.
if you have some license for running 10, what do you say that some 8 simulations at a time, you can run. If you have the limitations of only 4 files at a time, you can run only 4 simulations at a time. You cannot run above that.
Right.
Okay, this have some limitations. This have some limitations.
Yes.
Okay, and then I hope I have explained you about the transformer energization here. Okay, how to perform this random for what you say that random switching to see the transformer energization. Okay,
Yes.
and important thing which we have to which we have to record during the transformer energization is 2 values, right?
Current
During
and
which we
voltage.
have to record during the 2 is that one is the inrush current. Okay,
Yes.
inrush current, which is I have shown here, right? I
Yes.
have put the instantaneous current as yes, and then next is that RMS voltage. Okay, RMS
Yeah.
voltage is what you have to measure.
Yeah.
Okay, and then the next value is like instantaneous voltage. If you want, you can keep it as yes.
Yeah.
Okay, if the system has what does it generally happens during what do you say that during transformer energization is like this voltage, no, this RMS voltage, right? This
Yeah.
RMS voltage will be getting dipped, right? It will
Yeah.
just drop due to this
Yeah.
transformer energization.
Energization. Yeah,
Okay.
because that will draw the current. Yes.
Yes, it will draw some huge current, so my voltage might drop, right? But
Yes.
due to the presence of some harmonics in the system,
Yeah.
okay, some voltage harmonics in the system, what happens is like this, there is a chance like this what do you say, this voltage might increase.
Yeah.
Okay, if it is just an RMS voltage, what you say that without any harmonics, then there will be a dip in the system. But
Yeah.
when you have some harmonics in the system, what happens is like during this transformer energization, the chances of getting the peak voltage will be higher. Okay, that is why we are doing, that is why we are performing this transformer energization.
Yes.
Okay, I hope up to this point you are clear. Okay.
Yes.
We have seen transformer transmission cable modeling.
Yes.
Okay, we have seen cable modeling. We have seen transformer modeling, transmission line modeling,
Yes.
and source we have seen,
Yeah.
and reactor we have seen.
Yes.
These are all the basic equipments which we want to model for performing the TOV and SFO studies.
Okay.
Okay.
Yeah.
How to create a fault also we have seen, right? How to create a
Yes.
fault,
Yes. Yes.
that we have seen, right? These are all the
Yes.
basic types of basic models which we want to perform the TOV and SFO studies,
Okay.
like temporary voltage and the slow front over voltage studies. Okay, these are all the main, and we will see some basics about how what are all the types of scenarios which we have to create for performing these studies,
Yes.
for performing the temporary over voltage and slow front over voltage. I hope Silva sir might have
Yes. We discussed the TOV and SFO.
temporary voltage and slow front over
Yes.
voltage too. Yes,
Yeah.
yes. You might have some idea about the TOV and
Yes.
SFO, right?
Yeah.
Okay. Can you tell me some things about that? What we used to do perform and what we have to do?
For the TOV, we talked about the Faraday effect, and
Ah,
yeah, and then for the
yes.
SFO, and these we talked about line energization, reactor energization, transformer energization.
Okay.
Yeah.
And for TOV, you might have also heard about some load rejection cases.
Yeah, sorry,
Fault.
load rejection and fault as well. Yeah, yeah. Sorry,
Yes,
yeah,
yes,
load rejection and
yes,
fault. Yes.
yes.
See, for this the PS card you were showing on the screen. If you go to
Yes.
that page again, I have a question on this.
Yes.
So if you go to that control system down where you were incrementing your value, you know, that circle type where you written D, this,
Here.
right?
Yes.
Yeah. So if you double click that, you need to feed some kind of value here, or just a, right?
Yes,
Right.
yes. It is not a value.
Yeah.
It is to shape up the things, right?
No,
Here,
because you are saying when you are saying you are sending bit close one in this control system, and then you are also sending bit close 2t to increment that value, bt close 1, and you are receiving output as a bt close 2. Is that right?
yes, yes, yes.
So yeah, so my doubt on this is like how this system is incrementing those values. Do we know, or do we need to specify, or?
No, no, no. We don't want to specify. What I'm telling is like for BT close, what it does is like we
Yeah,
have chosen some 5 values, right?
yeah, it receiving from the signal. Yes.
Just it will just to get a receive from this. Just wait for me.
No problem.
It might have got the value like 0.5 0.53 or something from the random value.
Yes.
Okay, this will be the first value which will be going through this BT close one.
Bt close 1. Yes, I got it.
Okay, now
Yeah.
BT close to T, what will be the value is like it will take some values between the range
From
which we
random
have
that. Yes.
specified like
Yes.
2.3.
Yes.
Okay,
Yes.
from this it will get the value, and
Yeah.
just it will get incremented from this value
Inside that box, right? I
inside that
understand it.
box.
Yes. I
Okay.
thought we need to put like some kind of value in there as well, but I understand it now.
No,
Yes.
no. It is just a box. It is just an what do you say? That
Yeah.
it is just a module to add
Yeah.
something or yes. Here,
Yes.
if you want to add some lot more values, what we can do is like we can enable all those
Enable
things.
further channel. Yeah.
Further things, and we can add with this multiple what is it, this summation, using this summation.
Okay. I understand. Yes.
Yes, this is what we will be doing. Yes.
Are we going to run this case and see, or?
No, it will take some a long time to run.
Okay.
Okay, if you want to run, we can do simulations like
You can disable the multiple run, isn't it? And then
yes, we can disable the multiple run, but without multiple run, we can disable the multiple run, and it will take some random values.
Yeah.
It is throwing some errors.
Then you need to specify time in
Venkatji,
breaker.
we have deleted the surgers since the HCA energy.
Yes. I hope that are all the data which has been shown. Yes, error. If we delete all those data, then it will show. My screen is visible to everyone, right?
Yes.
Yes. We might have changed some data, I hope, for this particular thing. Just wait a minute. Just wait a minute. I will take the source file and I will run. Okay.
No problem.
Yes. hope my screen is visible, right? Hello?
Yes, yes, I can see it. Yeah.
Can you see this? I
Yes.
have just to run the same simulation file. Here you can see this the interest current which is happening in the system. Right? It is in
This is
it is in KA. It
ampere?
is not in
Right.
it is not in ampere. It is in KA.
Okay.
Okay. How
Yes.
to change that? It is in KA.
Okay.
Okay. It is also in KV.
Yes.
Why this? Before doing any simulation, kindly ensure that your breaker open resistance is somewhat equal to 10 e power 20 or something. Okay.
Okay.
Because what it does is like sometimes there might be some voltage will be going to them. If you see some voltages before any operations which you are performing, here you can see the difference, right?
Yes.
Before this, it is like there is some waveforms coming. Okay. This is the voltage
Yep.
at the instant when the transformer is getting energized. Okay.
Yeah.
And this is the interest current which is happening in the system.
Okay.
Like this, we can perform the transformer energization for a simple system. Okay,
Okay.
with one single transmission line or cable,
Yeah.
and with a single transformer, we can perform the transformer energization, or we can replace this transformer with a reactor, and we can perform the reactor switching. Like this, we can perform the simulation.
Okay.
Okay. Okay, but for if you are performing transformer energization like that and all, make sure you are maintaining the solution time step between 5 to 10. Okay, 5 to 10 microseconds.
Okay.
Okay, 5 to 10
Yeah.
microseconds. But if you are performing some TOV studies, temporary voltage studies, then it is not an what do you say that it is not on high frequency, so we can go with some 100 microseconds or 50 microseconds we can go.
Yeah.
Okay. We will see some basic about I hope temporary voltage Zar might have explained, right?
Yes.
Just wait for a minute. Can you see the definition between the power
Yes.
frequency voltage, temporary over voltage, and slow front over voltage, right?
Yes.
Okay. For power frequency voltage, what we do know, like it is the general frequency, like 50 hertz or
Yes.
60 hertz is
50
it
hertz.
is the power
Yes.
frequency voltage we used to say, right? And
Yeah.
for temporary over voltage, what is like power frequency over voltage of relatively long
Long duration.
duration. Okay, TOV can be observed due to load rejection, line fault,
Fault.
and transmission line, what is it, like current
Defect.
effect,
Yes.
like fault with load rejection. With that and all, we can see the temporary over voltage.
Yes.
Okay, temporary over voltage or oscillatory over voltage, which have a relatively long duration, more than few cycles. Okay,
Yes.
these over voltages can be undamped or weakly damped. Okay, so what is the time period? At what time period we have to measure the temporary over voltage? Whether we need to see the peak voltage which is happening during the load rejection, or else what we have to see? that we have to show, that we have to be very sure. At what instance we have to measure the voltage? At what instance we have to measure the voltage? If you have any idea, I can share, or else I will show you some. Yes.
We have to measure for full like cycle. Is that what you mean?
No, I will show. This is some cases which we have performed. Okay. Here, can you see this? Can you see this waveform? This is a load rejection scenario. Okay.
Yes.
Hello. This
Yes.
is a load rejection scenario for 400 kV bus energized. Actually, we are trying to create a scenario where the load has been rejected when the system is operating in a normal condition. Okay, we have created an instant at the load rejection instant at 0.4 second. Okay, 0.4 second. Just wait for it. Here you see it. Yes, here we can see this. Here we have created a low rejection scenario. Here, can you see this? At 0.4 second, we have created a low rejection scenario.
Yes.
There is a slight increase in voltage, right? Here, in this particular point. Can you see this?
Yes. There's a right here.
Oh. Visible
Yes,
to you.
I can see. Yes.
Yes, there is a slight increase in voltage. Okay, but what is the definition is saying? What is the definition is saying?
For a longer duration.
For longer duration, it should exist, and we should not record the instant like it is happening now. Okay, we should not record at this instant. What we have to do is like we have to record the changes after some 100 milliseconds or 200 milliseconds. 200 milliseconds would be fine. Okay, so that what we have done, we have measured the instant after 200. What we have here, you can see this. We have measured at 0.8 to 0.1. Okay, now the waveform has attained a steady state, and we have to measure the voltages at this point only. You should not measure for the complete duration. Okay, complete duration. This is what your definition also saying. Power frequency over voltage of relatively long duration. Can you see this? Relatively long duration. Okay, we should not see the instant at which the load has been rejected. Okay, it should happen for the long duration. Okay, TOV can be observed during these are the cases which we have created. Temporary over voltages or oscillatory over voltages which has a relatively longer duration. This is what I am saying. For more than few cycles, it should happen for more than few cycles. Now here in this case, which we have to, here you can see this. It is happening for more than few cycles, right?
Yes.
So this is where we have to measure the voltage. Before this, at the instant, we should not measure the voltage. Okay, for whenever we perform temporary over voltages. Okay, this is one scenario where I have measured for the load rejection case. At this condition, what I have done is like line to ground fault has been happening, and at some 100 milliseconds, at 100 milliseconds, the load rejection has been happened. Now what happens? Now my voltage will increase, right? And here you can see this. I have measured the voltage after this oscillations has been steady, the oscillations has been steadied out. Okay, like this only we have to measure the voltage. We should not measure at the instant where we are creating the scenario. Okay. This is a key takeaway for the temporary over voltage case. And for slow front over voltage. Okay, for slow front over voltage, what is the definition they have given? Transient over voltage, usually unidirectional, with the time to peak. What is the time to peak?
20 microseconds
to 5000.
Yeah.
It will be the main difference for the difference between different types of over voltages which is happening in the system. Here you can see this. Here the time to peak is only 0.1 microsecond. Here it is in it is in 20 to 5000, but it is only 0.1.
Yes.
Okay, it is only 0.1, and the tail duration is like only 300 microsecond. Okay, where we can see these things and all. Here they might have explained in the standard, right?
Part 1. Yes. in this one as well, I think. Yes, this one.
Here you can see this. For low frequency voltage, what is the waveform looks like. For transient, what is the time to occur this low front voltage, the peak time that has been taken by the particular waveform. That we can see it in the see it here. Okay, this is the main difference between the slow front over voltage, fast front over voltage, and very fast front over voltages.
Yeah.
Okay. Yes. This is the main difference between this case and that what I have to do. Yes, we will go into the scenario. Okay, we will go into the scenario. Okay, before Gopalji, Gopalji, hello, Gopal.
Yes, G. Yeah.
We might have created some cases for this LNT insulation formation problem, right? For temporary over voltage, slow front over voltage.
Yes, G. Yeah, the
Okay.
PSCAD model or
No. I want the cases today. Sorry, if you have some PSCAD model, no.
yeah, I have the PSCAD model.
Oh, okay.
Okay. Yeah, I can do it. Like, just a minute.
The meantime, I will search for that. If I have, I will project it. Okay.
Yeah. Venkatji, can you see my screen?
Just
Not yet.
Yeah, fine. So are you talking about this, G?
just no, the screen has been not updated. Google.
It's loading,
Just
but it's
wait.
not.
It's loading, but it is not visible.
Even Biscuit is
Okay.
Parle-G, so why not Venkatji and Biscuit also got G at the end.
Gee, okay.
Fine.
Sorry if I am taking your name. I don't know what your age is, but since I came in this country, so everybody used to say name. When I came here, I used to say sir, and they're like, no, don't call me sir. You can call me name. So even someone is like at my dad age or grandfather age, I just need to say like by name.
Okay.
Yeah.
Fine.
So I used to say like sir and madam when I was in SES India, but yeah. Beyond the immigration, then I just say name. In America, they also call their dad using their name.
Yes.
I was in
culture.
SES. Yeah, here is not. Here is they say like dad and papa or dad mostly. But I was in Canada and I see like the company owner daughter saying like, oh, hi Farid. And I'm like, oh.
Yes. Whatever the question he might be in, we have to call him with a name, right?
Yeah. Yes. That's how it works. Yeah. Doesn't matter you are talking to a director or owner or whoever. Yeah. And same in like your locality or shop. I can't say like to my neighbor like uncle or something. They feel like you are becoming personal and it's like offense. Yeah.
Yes.
Opposite to our culture. Yes.
Yes. Opposite.
In our culture, you can easily say like brother to anyone. It's not a
Yes.
big deal. But if you say here, it means you are becoming personal to him. So,
yes.
Okay. Now you can see my screen, right? Like it's loaded or?
Yes. Yeah. I can see.
Yeah. So
yes, it is. Gopalji, before that, can we show him the SLD and how we have differentiated the cases for different level of substations, right? Here we have 400 kV substations, and here we have 220 also, right?
Yeah.
The SLD is what I'm asking.
I've been through that file given by you, Venkat and Gokul, for a TOV.
Yes,
and
yes.
SFO.
Okay.
So I understood
Yes.
what you have modeled and how you have modeled, but
Yes.
then I was not able to run that because of some cable and transmission line embedded as a DLL file or something. I think Ramesh has that screenshot if he took. If not, I will run again in my personal laptop and I will give you the error screenshot.
Okay. Gokulji, you
Last
have
time
you
we have
seen?
shared that transformer actually. Correct. No,
Yes,
I
sir.
guess
Okay.
like that model is probably linked with some other file which we have not shared with.
Yes.
Sir, for
I will anyway.
running.
I will take a screenshot today and then I will send you.
Okay.
Right? It's fine.
Because for running TOV and SFO, we don't need any support files to run.
No, SFO was not able to run because the surge arrestor text file was missing, which was a small thing,
Yes,
and I
yes. That,
understand that.
yes,
But
yes.
for another
Okay.
one, I didn't understood. It was some DLL cable.dll file missing or something. But I will run it again and I will give you a screenshot.
Okay. It's not an issue, right? Yes, Gokulji, you can start the basic.
Fine. Okay. So this is our system. This is LNT our system. So basically we have OHL. This is OHL. Like, can you see my mouse pointer, right?
Yes.
Yes, we
Yeah.
can.
So this is OHL, and RAF super is the cable.
Yes.
So we can just concentrate only on cable. So let us concentrate on cable and like so. So this is cable. Like G30 is we have a cable, we have a OHL, and we have a reactor, we have a transformer.
Yes.
So this is basically our SLD. So I'll just give you an overview of this. So we have three transformers and we have three cables and like under OHL. So first thing for if you want to talk about TOV, first thing you have to know what all the equipments I'm having in my system, and based on
Yes.
that you have to derive your cases.
Okay.
So the first thing you should know what all the equipment, like I have a transformer, I have a OHL, I have a cable. Then the next step it will be you have to extract or you have to come up with different cases. So I just show you the cases. Just a minute. So these are the cases. So first case was Ferranti, like using I just open it. So this is the OHL. So can you see the PSCAD model? Hello, Himanshu?
Yes, Gokulji, we can see the
Yes. I can
PSK.
see it. Yes.
Yes, we
Yeah.
can.
So this is the OHL. Like I'm just going to highlight this. So this is the OHL,
Yes.
and so just go into yeah. So the Ferranti effect, basically, what is Ferranti effect? Do you have any idea on Ferranti effect?
Yes. The receiving end voltage will be higher due to some capacitance
Mhm.
of the line.
Yes. So the same thing we're going to do. This is just a module. So if you just double click it, you'll get this full subsystem. So here I'm going to measure the voltage. So in this bus, this is 400 kV bus, and I'm going to measure the voltage here, and also
Okay.
I'm going to see the RMS of RMS. This is peak. So the V
Yes.
bus is peak, and so can you see this, right?
Yes.
So I just zoom this. So I just want to plot two things. The first one is the peak value, and the second one
Yeah.
is the RMS value.
Yes.
So since the RMS is the single phase, right? So this block itself and single phase RMS.
Yes.
So the output of this one is the three phases. So I need a converter, something like this, and I have to
Yes.
convert the three phase to each single phase, and then
Yeah.
I have to check the RMS voltage. So that's
Yes.
why I've used this block.
Yes.
So this one is the peak value. So just let me run this, and we can just simulating this. That's it. Yeah, it's simulating this.
Himanshu, before going for that, I have a question for you.
Yes.
Why we do need to perform this temporary overvoltage study? That we have to answer, right?
To find out the continuous rating of surge arrestor.
Yes, whether your surge arrestor, what we
Yes.
have to do is like we have to find out what is the maximum voltage which is happening in the system
Yes.
during this power frequency changes like load rejection like that. So
Yes.
that what we have to make ensure that your the particular surge arrestor which has been
Yes.
selected should not act for this type of conditions, right? That is
Yes.
what the main point which we are going to make sure by performing that temporary overvoltage.
Yes.
Okay.
Yeah. So so we have simulated this. So this is the RMS voltage. Like, you can notice the difference, right?
Yes. Yes.
So this is RMS and this is the
Yeah.
peak. So
Peak.
like I've just measured from I'll show you. I just measured from 0.5 to 1.
Yes.
So the over voltage is 337.670. Like,
Okay.
yeah. So you get the point. Like why
Yes.
I have got 337.670.
Yes. Because of the Faraday effect. Yes.
Yeah. Like, I'll just show you 400
Divided by.
square root square root.
2.
So I'm sorry. By root 3. Thank you. Sorry. I just 1 minute. 100 divided by root 3. Right? So 230 into root
That
2.
multiplied by 8. Yeah.
Into so 326. Like the normal voltage, if I say 400, then the peak should be 326.59, right?
Yes.
So we have to check whether like we having some increase. We having some over voltage due to this Ferranti effect. Like this
Yes.
voltage should be 326,
Yeah.
but we are getting 337. This is
Yes.
peak, right? So
Yes.
we can talk about the RMS voltage. Like the RMS voltage is 238.75.
Yes.
So
Yes.
you have to check all the phases. Like this is the A phase,
Yeah.
this is the B phase, this is the B phase, and this is the C phase. So
Yeah.
out of these three phases, you have to see what is the highest maximum voltage in all three phases.
Yes.
So for time being, we can take 238.76 is the highest voltage.
Yes.
Actually, this is the voltage you should get, right? This is the
Yeah. 230.
RMS voltage,
Yeah.
like 400 bar loop. You should get 230.94, but you're getting 236.78. So we
Yes.
can conclude that like in Ferranti effect, there is an over voltage.
Yes.
Yeah, just like yeah, we can conclude that. Like if I'm going to do if I'm going to energize the like or say if there isn't Ferranti effect, then I'll get over voltage in my system. So there are
Yes.
different cases you
Go,
can do it.
go Suji, just
Yes.
for a confirmation. can you go into the source at what voltage we are performing the study? We might have kept 1.5, 1.05 per increment in voltage, right?
This is for yeah 400.
420, yeah, 1.05.
No, no. This is the OHL. This is 400, and this one we have kept off. So this, if I say 1 year, then this breaker is normally open. So this will not comes into picture.
Come into picture.
So, so this is the OHL, and this is the sorry, this is the OHL. So this is what we have to consider. We have considered only the system voltage, 400 kV. Yeah.
Okay.
Yes. So there are different cases. So the same thing is this is load rejection. Third case, the load rejection. The same thing. So we just go into this. So I have connected a load over here, and I'm going to. So there is a breaker, and I'm just going to disconnect the breaker at 0.4. So actually, this model we have seen, right? Like not on the full thing, but we have modeled it, right? How to reject a load and yeah. So the same thing. Only thing is we are measuring the voltage over here, and the same thing we are measuring the RMS voltage.
Yes.
So there are different cases we can perform. So I'll show you the different cases.
The magnitude of load, how do you select that? Just from the transformer data itself, or from a client email, or how did you select it? How much load you want to reject?
We took 500 MVA itself. The transformer load, yeah.
Okay.
We just took that 500 MVA and we just rejected that load.
Okay.
So this is per phase, right?
Yes.
That we have to get it from the customer, Himanshu. At what is the load that has been connected in the system, that we have to get the detail from the customer.
Okay. Yes.
What is the megawatt of load that is connected in the 400 kV side or 220 kV side? That detail we have to get it from the customer, and we have to model the particular load as a constant power load.
Yes.
Okay, here you can see this, all the terms have been kept at 0, right? Then it will act as a constant power load, right? We have took the load modeling session also, right? In that I might have explained. Okay, here we have modeled it as a constant power load, and the data, how much megawatt of data that we have to collect it from the customer. Okay, here we have kept the power factor as 0.95.
Yes.
Okay. 0.95 power factor, and we have taken a 500,000 megawatt load, I hope.
Yes.
This 1000 megawatt. Okay, this 1000 megawatt load. Okay, these details we have to get it from the customer, like what is the load which is connected in the system, that we have to get it from the customer. Then only we can perform studies.
Okay. So there are different faults. Like the next case is load rejection with fault. So I just open that.
This file already we have shared with Himanshu, right?
Yes, sir.
I have only one main file. Yeah.
Okay.
That was with the
we have shared,
yeah, you can probably practice it, or probably you can change it, and let's see if you have any questions. Also, we can discuss.
Yeah. First thing, I can't run that file because of some error, and I will take a screenshot and I will send.
Yes, means Venkat, rather than going for a cases, why not like ask Himanshu to share the screen and try to address what's the problem?
Oh yes sir, that is what I am telling, but I have muted myself. Yes sir, that is what I am trying to say. Himanshu, if you have that system, can you show me what is the error which is happening in there?
At the moment, it is in my office laptop, so I can't run it. But I have some questions which I want to ask.
Yes.
I still have the free edition here, so I can't run it. But I have some question on that.
Yes.
So that was TOV. So
Yes.
I understand how did you model that. The
Okay.
only thing is see, when you are modeling this like a subnetwork,
Okay.
what is the need of modeling it like that? Why can't you put this just in one screen? And how exactly you model these? For example, how did you embedded this whole block? I know you show me how to create component and put a subnetwork inside that,
Yes.
but how
Yes.
exactly you have done this, I have no clue. And then
Okay.
another thing is for example, these breakers again. So you model, again is the same thing.
Okay.
Another thing is this 0-1 numbering.
Yes.
How you decided like 0 for something and 1 for something. And
Okay.
I know it's
It
open
is-
close, but yeah.
Yes.
And yes, and other than that, this line you broken in two pieces. We discussed that just
Yes,
to create a fault in the middle.
to create a fault in middle of the line.
Yes.
To see
yes.
the impact what it does creating in the system. That is what I have done. Yes.
Yeah, so in there was same thing in SFO as well, like how you
Yes,
created
yes.
the subnetwork. But
Okay.
in this one, the only question I have is like how did you created the subnetwork using this line, and then what is the logic behind keeping this like? I know it's open close, but how you decide like which one is going to be open close? So that one. And for the reactor, you show me last time you going to model this as a saturable reactor, but here you just put that as an inductor. Is that right?
8.49 as a value, right? How I
Yeah,
have
but
modeled
here
this.
is just as an inductor, normal inductor.
Yes, just an
Not saturable
inductor.
reactor. Yes.
Yes.
Yeah. So these
Because
are the
what
questions I have on this one. Unfortunately, I can't run this just now, but I will run in my personal laptop and I will give you the screenshot of the error, because it was not running. Here it won't run anyway because of the free edition, but it was not even running in that particular one. And then for SFO, I just renamed the case because if suddenly open, so nobody knows what it is. So in this one, I understand again how you model this and what you have modeled based on our discussion. The only thing pending is surge arrestor, which I haven't seen so far. How to model it?
We will take it tomorrow. We will see how to model surge arrestor
but
tomorrow.
But in this one, the question is when you are assigning these node N1 bottom, N2 bottom, and this, and then I know you are calling them here. So it is a little bit confusing for me how exactly you are calling them. So if you explain that, then single line diagram itself is quite clear and it's understood. I understand. How did you model that? And the only other query was here. It was a disconnector, and you modeled this as a separate
disconnector, right? Yes, it is a disconnector.
Yeah. So I understand what you have modeled here and how you have modeled, but the A thing is I need a little bit explanation behind these 1 and 0 and how you are controlling them.
Yes.
Because I can't see any control here.
Yes. That is just a simple breaker, Himanshu. Just go inside there.
Yes.
It is just a simple breaker. Okay, it is normal break which we have chosen. Okay. If we choose this is a simple way to represent a breaker, whether it is a closed or open. Okay.
So
if
one is closed.
It is one. It is open. One means open.
It's not conducting, right?
Yes, it is not conducting. Okay, 0
so
means
green
it is
not
closed.
conducting.
Yes, green is not conducting, and red is like if we keep it as 0, then it will be in a closed position.
I was thinking it's opposite.
Okay.
Yeah, but if you explain me how you call these nodes, that would be great.
Okay.
That's a key challenge faced in this one.
Yes.
I didn't dedicate it a lot of time, to be honest, but yeah, I tried to understand it for few hours, but I was a little confused on that. And same here, like how exactly you are calling these node inside that big box, and when you are created this itself, so what kind of node you give to these wires? Like it just like when you created this block, for example, and when you put this all inside, So these are just wire, or these are like,
It is just a wire. It is just a wire. You
Okay.
can see there is wire mode, right? With the wire,
Yeah.
I have joined two nodes.
Yeah.
Okay,
Yeah.
the node which is there and the node which is here. Okay.
Yes. So
I will
how
give an
did
idea.
you component inside this? Yeah, it is crystal clear to me. I
Yes.
understand it. And same here and
Okay.
same here. The only thing is, how
Okay.
did you put this all picture together? That's what I want to understand in SFO
Okay.
and subregister, of course.
Yes, I will tell you. Just to go inside this. Just to
The
go inside the central substation. Central substation. I will show you. Yes, just to zoom out. Just to zoom it out. Just zoom it out.
Yes.
Okay, this is the main breaker system which we have shown, which we have seen in the SLD, right?
Diagram.
Which we have seen in the SLD, right? In single line diagram, we have seen that. This single line diagram, we can conclude that from the single line diagram, we have like 3 cable incomers, okay,
Yes.
and 2 transmission line incomers, right?
Yes. Yes.
Okay, for that, what I have done is like here I have took some 5 nodes, right? Here in the upside part, you can see this. There is something node 1, node 2, N2 top. Can you see this?
Yes.
Yes. For that I have decided like I have some 5 incomers in my system, so that I have took some five nodes. Okay,
Yes.
1, 2, 3, 4, and 5.
Yeah.
In the upside part, right?
Yes.
So that my incomer part has been completed, right?
Yes.
Now I have something called as outgoing part. From this
Yes.
particular outgoing means it is outside the GAS substation. Okay.
Yes.
For outside the GAS substation, I have 3 transformers, right? I have 3 transformers, and I have about 3 reactors.
Yes.
Right. So totally 6 outgoing, right? So that with that I have created some 6 nodes, 6 bottom nodes. Here from the left you can count it.
Yeah.
1, 2, 3, 4, 5, 6 nodes I might have
4, 5,
created.
6.
Okay, with this idea I have created this block.
So you created a create component, and then you went here, and then you created 3 top channel and 6 outgoing channel. Is that right?
6 outgoing periods. Yes. Like that I have created, and I have remodeled this structure for my the better view.
Right, and then when you came here, right, and then you modeled of course the source line, fine.
Yes.
And then again you calling this as an
incomer to my substation. It is
this node has to be N1 and N2 should be the same based on SLD pointing towards 400 kV. Is that right?
Yes, it should. What do you say that it has to it has to go and connected in a particular what do you say that particular dia which is explained in the SLD.
So the N1 bottom and N2 bottom.
It is just a node. It is just a node.
It should be the same name here. Is that right? Or not?
No. It is not necessary. It is not necessary.
So how this program knows that you are going to connect this particular overhead line on a particular bus bar?
Yes,
here.
How we have created. Yes. For that I will give explanation. Just double click this central substation.
Okay.
Just double click this central substation. Okay. Yes. This part we know there is something called as graphic part, right? Just to go inside this graphic part.
Yes.
Just to zoom it out.
Yes.
Okay, here you see this. There is something called as N1 top, N2 top, N3 top, N4 top, N5 top, right?
And six outgoing. Yes, that I understood. Yes.
6 outgoing. Okay, now what I have done is like if I connect this module with the other module which I have created above. Okay, what it really happens is like this N1 top will be joining in the N1 bottom of the above module. Okay, when I connect this thing with a wire in outside, okay, just to go outside the schematic, just to go.
So I know that you are trying to connect this N top 3 to the
with the N1 bottom of the above module.
How did you done that? That's the question. Yes.
Yes. In the graphics, can you go inside this graphic? Here I have created a N1 bottom and N2 bottom, right?
Yes. Yeah.
Okay. Now just come here. Just come outside. Just come outside.
Yes. Yeah.
Again come outside. Again come outside.
Okay.
Now what I have done is like I have created this 400 kV T2 module. Okay,
Yeah.
I have kept 2 outgoing from this particular module.
Yes.
Two module, right? This particular is like this is N1 bottom and this is N2 bottom, right?
Yes.
Now what I have to do is like I have to connect this module and this module through a wire. Okay,
Yes.
because
So
the module
if I
we
connect
have
this through wire, yes, please.
through it is an electrical module, right? We
Yes.
have created it as an electrical module, right? This is an electrical module. Okay, both the things. Then when we connect it with an wire, what it does happens is like the connection will be taken from that module to this module.
Okay, so inside here, these 2 wire will get automatically connected to
the this N2 top. Yes, here it will be automatically connected to this particular area.
Why not on these 2 and why not on this one?
Yes, as I said, it is the graphical view, right? It is the graphical view, right? In this graphical view, what we have to do is like we might have assumed the particular this N2 top for the transmission line.
Okay.
Hello.
Yes.
Okay. That is the plan which we have in our mind, and like that only we have constructed this module, right? We have constructed this module, right?
Yes.
With that, what I have to do is like I have to go into my SLD. Okay, I have to go to my SLD. Then I have to see like what I have to do is like at what point my OHL is getting connected to this. Okay.
What I will do is I will try to create this on my own. I mean, I will copy paste, of course, your diagram, but I will try to create this scheme here to have little confidence, because I know how it is working, but I am not. I was not exactly sure like how exactly you are calling this node, in this diagram, and same how you are calling these 3 nodes in this diagram, or how you are sending these nodes to this diagram.
These diagram.
So
okay.
Yeah. So that what I didn't understood from this one. And the only problem in this one, when I was running, it was saying the surge arrestor text file was missing. So of course I can see that for this one I don't have this particular file. So that's why So that's why it was not able to run. Yeah. But for this one, there was some weird error. I don't know. I don't remember what it was, but it was saying some transmission.dll or cable2.dll is missing and abnormal run terminated or something. But I will take a screenshot and I will. And the only thing then you need to tell me is a logic behind this.
Okay. That I will explain. Tomorrow I will explain.
Rest is very clear to me. Yes, rest is very clear to me. I understand what you have modeled.
I will explain it this with an paint. This is paint. With paint, I will explain that. Okay. I hope that.
And also how to create this like some mask, some network.
Yes. Okay.
In the module, I know. In that create component, I know, but I'm not sure like here like how do we do that?
I have created different designs. Okay. That I will show you.
Yes. So this is only from my side. Yes.
Okay. That I will explain it tomorrow with a paint. That then you will be very clear about that.
Okay.
That
would be clear.
Yes. Thank you.
So
if you have any other doubts, this is all we have planned for today. Okay, tomorrow.
No other doubt. It's good. The only thing remaining is the surge arrestor, and then we will see that.
Yes. Surge arrestor we will see tomorrow. How to model a surge arrestor for different studies, like for SFO how we have to model, and for lightning studies how we have to model. Okay, that we will see tomorrow, and after that we will see some cases for SFO and TOV. Okay, and we will come up with some plans tomorrow. Okay, to engage. Yes.
Okay. I will run that, and I will collect the screenshot for you so that you can help me out why it is not running.
Yes. Okay.
And after this week class, then I will try to create the same thing on my own, and I will see where I.
Okay. Yes.
Yeah, because after a few days you will disappear, and then.
If you have any doubts, you can message us.
Yeah.
Any
doubts, even after a month like this.
If you have any doubts, you can message us, and we will surely answer your question. Okay.
Yes. Thank you, guys. Thank you for your time.
Thank you,
Much
So 1:30 India time, right?
Say again? Yeah, tomorrow 1:30. Yes.
1:30.
Yeah.
1:30 India time. All right. Very good.
Yes. Okay.
Okay.
Thank you so
Okay.
much.
Thank you.
Yeah.
Thank you.
Bye-bye.
Thank you.
Safin.
Thank you all.
We can stay here for a minute. Like we have some small discussion on LNT project.
Okay, sir.
Okay, I will drop
Okay.
call. Okay, no problem.
Yeah.
Okay.
Yeah.